In December 1941, an ordinary foreman at Ford, as illustrious River Rouge plant in Dearborn, Michigan, found himself utterly bewildered by the technical drawings laid out before him. Instead of the familiar specifications for a V8 engine block, his gaze was fixed upon schematics for a formidable 30-ton steel behemoth, armed with a powerful 75mm cannon. This dramatic shift occurred mere days after the devastating attack on Pearl Harbor, signaling an unequivocal directive from the United States government. The very assembly lines that had, until recently, busily produced sedans and coupes were now commanded to commence the immediate manufacture of tanks. This transformation was far from a gradual evolution. The newly formed Automotive Council for War Production, established in early 1942, issued a stark decree to Detroit's industrial titans, Ford, Chrysler, and General Motors, that all civilian vehicle production would cease entirely by February 1942. This left an astonishingly narrow 2-month window for these corporations to retool factories valued at hundreds of millions of dollars, an undertaking of immense logistical complexity and financial commitment. Chrysler's ambitious tank arsenal, situated in Warren, Michigan, had already broken ground in September 1940, even before America officially entered the global conflict. Spanning an expansive 113 acres of what was once tranquil farmland, this colossal facility swiftly sprang to life. By January 1942, the inaugural M3 Grant medium tanks were triumphantly rolling off the very production lines where Dodge trucks had been meticulously assembled just a few months prior, a testament to the unprecedented speed and adaptability of American industry. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please leave a comment about where you are from and what you think about the video topic. The strategic rationale underpinning this profound pivot from automotive manufacturing to armament production was remarkably straightforward and pragmatic. Automobile manufacturers inherently possessed 3 indispensable ingredients crucial for the large-scale, efficient production of tanks. Firstly, they commanded immense physical infrastructure, sprawling buildings equipped with sophisticated overhead cranes, robust power systems capable of simultaneously running hundreds of heavy machines, and extensive railway spurs facilitating rapid transportation of materials and finished products. Secondly, their mastery of high-volume manufacturing surpassed that of any traditional armaments company. While esteemed European firms like Krupp in Germany crafted exceptional tanks, their production methodology often resembled that of skilled artisans. Detroit, in stark contrast, engineered its products with the ceaseless, standardized flow of a mighty river, continuous, relentless, and uniformly precise. Thirdly, the existing workforce already possessed invaluable expertise in working with steel, operating powerful stamping presses, and meticulously fitting thousands of intricate components into a single, functional machine. However, what truly rendered this industrial metamorphosis genuinely revolutionary was not merely the repurposing of car plants for tank production. Rather, it was their optimization for this new purpose in ways traditional arsenals could never achieve. The Fisher Body Division of General Motors, typically responsible for stamping out car bodies, became the primary producer of the M4 Sherman's crucial hull sections. They approached 5-inch thick armor plate with the same analytical rigor and production techniques previously applied to sheet metal for Buick hoods, treating it as raw material for their colossal hydraulic presses. Chrysler engineer Bob Gregory later recounted that the paramount challenge was not the inherent technical complexity of tank components, but rather the arduous task of convincing workers that a weld on a transmission housing demanded the exact same unwavering precision as a critical weld on a tank's final drive system. The sheer velocity of this industrial conversion continues to astound. The Chrysler Tank Arsenal, for instance, delivered its first M3 Lee medium tank in April 1941, an astonishing mere 7 months after initial construction commenced. Ford's historic Highland Park plant, the revered birthplace of the Model T, was already churning out robust tank engines by March 1942. The entire intricate supply chain underwent a radical reorganization within a matter of months. Steel mills rapidly recalibrated their rolling schedules to produce the significantly thicker plate required for armor. Rubber companies swiftly redirected their output to the specialized components needed for tank tracks. Concurrently, electrical manufacturers shifted their focus from producing car radios to manufacturing essential turret motors. The industrial feasibility of this monumental undertaking was largely underpinned by a pervasive commitment to standardization. The Sherman tank, from its very inception, was meticulously designed to be manufactured within existing car plants. Its visionary designers at the Aberdeen Proving Ground engaged in direct consultations with automotive engineers in 1941, posing a question that no military procurement officer had ever seriously contemplated before. How can we design a tank that can be efficiently constructed using established car manufacturing techniques? The innovative solutions included features such as bolted rather than welded turrets in early models, ensuring interchangeable parts across various tank variants, and engines that mechanics, already proficient in servicing trucks, could readily maintain. Franklin Roosevelt, with profound foresight in 1940, grasped a fundamental truth that would ultimately define the entire war. Factories win wars with the same decisive certainty as soldiers. On December 29, 1940, a full 11 months prior to the attack on Pearl Harbor, he delivered his iconic Arsenal of Democracy fireside chat to an audience of 60 million radio listeners. This evocative phrase was far more than mere rhetoric. It served as a comprehensive blueprint for transforming America's formidable industrial capacity into a weapon more devastating than any bomber or battleship. Roosevelt articulated production targets that, at the time, seemed utterly preposterous: 50,000 aircraft per year. Considering the entire U.S. aviation industry had only managed to build 6,000 planes in 1939, he demanded tanks, ships, and artillery in quantities so vast they would metaphorically bury the Axis powers under an overwhelming weight of material. The primary mechanism Roosevelt employed to achieve these ambitious goals was the War Production Board, WPB, established in January 1942 under the leadership of Donald Nelson, a former Sears executive with an astute understanding of supply chains and logistics. Nelson's WPB wielded authoritarian powers that would be entirely inconceivable in peacetime America. They possessed the authority to command any factory to immediately cease civilian production. They could meticulously allocate raw materials, steel, aluminum, rubber, copper, precisely directing which industries received specific tonnages. Furthermore, they could prioritize contracts, meaning a tank order would leap ahead of literally everything else in the production queue, ensuring rapid delivery. Yet a crucial aspect often overlooked by many documentaries is that the government did not merely commandeer these factories through patriotic speeches alone. They strategically employed compelling financial incentives that rendered war production irresistibly profitable. The cost-plus contracting system guaranteed manufacturers their production costs plus a predetermined profit margin, typically ranging from 7 to 10%. This ingenious system effectively eliminated all financial risk for the companies involved. If Chrysler, for example, invested $100 million in constructing and operating a tank plant, the government fully reimbursed every single penny and added an additional $7 to $10 million in profit. Traditional competitive bidding vanished entirely. The government's paramount objective was production speed, not cost savings. The Defense Plant Corporation, DPC, a vital subsidiary of the Reconstruction Finance Corporation, financed an astounding $9 billion worth of new factory construction between 1940 and 1945. They didn't simply loan money, they built entire state-of-the-art facilities and then leased them to manufacturers for merely nominal fees. The Chrysler Tank Arsenal, a prime example, was entirely government-funded, government-owned, and Chrysler-operated. Following the war, companies were granted the option to purchase these immense plants at incredibly bargain prices, a form of corporate welfare on a scale that undoubtedly made corporations salivate with anticipation. General Motors alone received over $10 billion in war contracts between 1940 and 1945, an amount roughly equivalent to $180 billion in today's currency. The intellectual framework underpinning this massive industrial mobilization originated from economists who had meticulously studied the production failures of World War I. In 1917-1918, the United States had stumbled into war with virtually no industrial coordination, leading to severe shortages, crippling bottlenecks, and widespread profiteering scandals. Bernard Baruch, who had successfully managed Wilson's War Industries Board, wisely advised Roosevelt to avoid these past mistakes by establishing centralized control from day one. The WPB did not passively wait for shortages to manifest. Instead, they proactively forecasted needs 2 years in advance and meticulously allocated resources accordingly. Labor was mobilized with equally impressive precision. The War Manpower Commission, established in April 1942, possessed the authority to direct workers into essential industries. Unemployment, which had stood at a troubling 14.6% in 1940, effectively vanished by 1943. Factories that had languished with single shifts during the Great Depression now operated 3 shifts around the clock. The government generously subsidized extensive training programs, rapid, intensive 8-week courses that taught welding, machining, and assembly skills to individuals who had never before set foot inside a factory. Roosevelt's true genius lay in his astute recognition that American industry's peacetime overcapacity, all those idle factories from the Depression era, could be brilliantly converted into wartime overcapacity, relentlessly aimed at the enemy. Every single Sherman tank rolling out of a repurposed car plant represented an industrial muscle that Germany and Japan simply could not match. Their factories were already operating at maximum capacity in 1939. America's, by contrast, were nowhere near their full potential. The Willow Run project was initially deemed an impossibility when Charles Sorensen, Henry Ford's chief lieutenant, announced in early 1941 that Ford would construct a factory capable of producing 1 B-24 Liberator bomber per hour. Aviation experts openly scoffed. Boeing and Consolidated Aircraft, established aviation giants, built bombers in small batches using highly skilled craftsmen. Sorensen, however, envisioned building them with the continuous flow and efficiency of Model Ts. The colossal facility that ultimately materialized in Ypsilanti Township, Michigan, became the definitive template for how America would manufacture everything from bombers to tanks. Yet, it nearly buckled under the sheer weight of its own ambition. Construction commenced in April 1941 on what would become the largest single manufacturing space under one roof, a staggering 5 million square feet, shaped like an L that stretched over a mile long and a quarter-mile wide. The building itself required an immense 440,000 cubic yards of concrete and 29,000 tons of structural steel. Ford engineers meticulously designed a production line where a B-24 entered as 450,000 separate components at one end and rolled out as a fully functional bomber at the other. The assembly line moved with astonishing precision. Every 63 minutes, one complete aircraft emerged. But here is what made Willow Run profoundly relevant to Sherman production. The exact same fundamental principles applied to tanks, albeit at different scales. While Ford did not build Shermans at Willow Run itself, the engineering philosophy perfected there rapidly disseminated throughout automotive tank production. Meticulously break down the complex weapon into manageable subassemblies, construct each subassembly on dedicated lines, and then bring them together at the final assembly stage with mathematical precision. The M4A3 Sherman variant, which famously utilized Ford's powerful GAA V8 tank engine, perfectly embodied this ground-breaking industrial thinking. The philosophy of industrial warfare, prioritizing sheer volume and standardized efficiency over artisanal craftsmanship, found its most complete and profound manifestation in the American manufacturing efforts of World War II. This strategic perspective, which fundamentally reshaped the landscape of wartime production, underscored a radical departure from traditional approaches to armaments, emphasizing the systematic assembly of vast quantities of reliable, if not individually exceptional, military hardware. This particular paradigm shift was not merely an abstract concept, but a deeply embedded operational principle that permeated the entire production apparatus, from conceptual design to the final assembly line, ultimately dictating the very nature of Allied logistical and tactical superiority. However, the initial phases of this ambitious undertaking were fraught with considerable difficulties, nearly confirming the dire predictions of those who doubted the viability of such a grand industrial experiment. For instance, upon its inauguration in September 1942, the Willow Run facility, a cornerstone of this new manufacturing ethos, managed to roll out a mere single B-24 Liberator bomber throughout the entire month. This dismal output stemmed from a cascade of systemic failures, a chronic lack of essential tools, the chaotic delivery of components in an illogical order, and frequent stoppages on the assembly line due to ill-fitting parts that defied integration. By December 1942, the cumulative production had only reached a meager 56 bombers, a stark contrast to the aspirational target of 1 aircraft per hour. This profound inefficiency and the relentless operational hurdles led to an alarming labor turnover rate, with half of the workforce abandoning their posts in sheer exasperation. Exacerbating these production woes were severe housing shortages in the surrounding areas, compelling many employees to reside in their vehicles or squeeze into cramped apartments, sometimes 10 individuals to a single unit, further highlighting the immense challenges faced. The pivotal turnaround at Willow Run was orchestrated by Sorensen, whose approach was deeply rooted in established automotive manufacturing principles, particularly emphasizing rigorous standardization and the widespread implementation of specialized jigs. His vision demanded that every single component adhere to exacting specifications, ensuring precise fitment on every occasion, a requirement that necessitated manufacturing tolerances measured with astonishing accuracy, often down to mere thousandths of an inch. To achieve this unprecedented level of precision, Ford engineered and fabricated an astonishing 7,500 distinct jigs, custom-designed fixtures meticulously crafted to hold individual parts in their exact predetermined positions during critical assembly processes, like welding or riveting. This ingenious methodology fundamentally revolutionized assembly, a complex wing section, which previously demanded hours of painstaking labor from highly skilled craftsmen, could now be swiftly put together by semi-skilled workers in a matter of minutes, thanks to these jigs that unequivocally guaranteed perfect alignment and positioning. This systematic elimination of part variation rather than relying on individual worker dexterity to compensate for inconsistencies proved to be the quintessential ingredient for success. While conventional aircraft manufacturers historically depended on the exceptional skill of their workforce to overcome inherent discrepancies in parts, Ford's innovation simply eradicated the source of the problem. This identical philosophy of precision jigging and standardization was subsequently applied with equal transformative effect to the production of the Sherman tank, demonstrating its versatility and profound impact across diverse industrial sectors. We invite you to stay with us and watch the end of this insightful video. Your support means the world to us, and we would be truly grateful for your like and subscription. Please also consider leaving a comment below, letting us know where you are from, and sharing your thoughts on the compelling topic discussed in this presentation. The efficacy of this jig-based manufacturing philosophy was equally evident at Chrysler's tank arsenal, where the construction of a single Sherman tank hull necessitated an astounding 5,000 individual welds. During the initial stages of production, this immense complexity led to significant quality control issues, manifesting as frequent weld cracks, noticeably misaligned armor plates, and hatches that failed to achieve a proper sealed closure. However, by the middle of 1942, a dedicated team of engineers had meticulously designed and implemented an extensive array of specialized positioning jigs for every critical weld point on the tank's hull. This ingenious intervention meant that even workers with a mere 8 weeks of focused training could consistently execute welds that not only met but often exceeded stringent military specifications, precisely because the jigs held every component in an impeccably square and stable configuration. Consequently, the tank's assembly ceased to be an intricate, often problematic, metalwork art project, reliant on individual skill, transforming instead into a highly organized sequence of precisely choreographed industrial steps, ensuring consistent quality and accelerating output. Ultimately, by 1944, the Willow Run facility triumphantly realized its ambitious potential, consistently achieving its long-sought goal of producing one B-24 bomber every hour, a rate that was occasionally surpassed. Throughout its operational lifespan from 1942 to 1945, the plant successfully manufactured a remarkable total of 8,685 B-24s, a figure that constituted nearly half of all Liberator aircraft constructed during the entirety of the war. This monumental achievement solidified a crucial lesson that resonated across every subsequent war production facility. Even the most daunting industrial complexity could be effectively overcome through meticulous process engineering, unwavering commitment to standardization, and, critically, an acceptance of an iterative development cycle. This involved the understanding that one might need to construct a significant number of initial, less-than-perfect examples, perhaps 100, before truly perfecting the 101st unit, thereby embracing continuous improvement as an integral part of the mass production process. In stark contrast to the American approach, German factories, driven by a different manufacturing philosophy, seemingly never assimilated this vital lesson of iterative mass production. Their methodology remained rooted in the endeavor to construct each tank to an exacting standard of perfection on its very first attempt, a process inherently antithetical to rapid, large-scale output. The Sherman tank, conversely, was intentionally conceived with a pragmatic design ethos, to be merely good enough for its intended purpose, a strategic decision that reportedly exasperated German tank commanders to no end. When the formidable Panzertruppen first encountered these American tanks in the crucible of North Africa during late 1942, they observed a profoundly peculiar and unsettling characteristic. These Allied armored vehicles were not engineered to surpass German panzers in terms of firepower or defensive armor. Instead, their design implicitly aimed for a far more insidious objective: to simply outexist them through sheer, overwhelming numbers and relentless availability. The overarching design philosophy behind the M4 Sherman was predicated upon a query that at first glance might appear almost cynical in its pragmatism. What constitutes the absolute minimum capability required for a tank that we can then produce in truly overwhelming quantities? This foundational question informed every subsequent design decision, beginning most tellingly with the choice of engine, which illuminated the entire strategic approach. The initial M4 models were powered by a Continental R975 radial aircraft engine, quite literally, an aero engine repurposed and bolted into an armored chassis. The rationale for this seemingly unconventional choice was brilliantly simple. The United States already possessed an established infrastructure for the mass production of radial engines for its burgeoning aircraft industry, meaning a robust and readily available supply chain was already in place. Subsequent iterations of the Sherman utilized alternative power plants, such as the Chrysler A57 multibank, an extraordinary assembly comprising 5 distinct automobile engines linked to a single drive shaft, or Ford's GAA V8, which was itself a significantly modified bomber engine. This stands in stark contrast to German tank design, for example. The formidable Panther employed the Maybach HL230, a highly specialized engine meticulously engineered exclusively for tank applications, demanding bespoke manufacturing processes. Consequently, when a Maybach engine inevitably failed, it necessitated specific, often scarce, Maybach-only components for repair. Conversely, should a Sherman's engine malfunction, its reliance on common or adapted components often allowed for the expedient cannibalization of parts from readily available trucks or other battle-damaged tanks, a crucial logistical advantage. In a similar vein of pragmatic design, the Sherman's primary armament, the 75 mm M3 gun, was intentionally selected for its adequacy rather than any perceived superiority in raw power. American ordnance officers, as early as 1941, were fully cognizant that this particular 75 mm cannon would be largely incapable of penetrating the formidable frontal armor of heavier German tanks. However, this limitation was not deemed a critical flaw, as it did not align with the weapon's intended strategic purpose. The gun was demonstrably effective at delivering high-explosive shells against entrenched infantry positions, capable of neutralizing medium tanks at conventional engagement distances, and perhaps most crucially, its ammunition was fully interchangeable with a host of other American military systems. This widespread standardization of ammunition profoundly streamlined logistical operations, enabling a single supply truck, for instance, to transport a uniform type of 75 mm shell that could be utilized across a diverse array of platforms, including Sherman tanks, M3 half-tracks, and various towed anti-tank guns, thereby drastically simplifying the complexities of battlefield resupply. The strategic choices regarding armor thickness further illustrate this consistent design philosophy. The Sherman's frontal hull armor, measured 51 mm in thickness, deliberately sloped at an angle of 56 degrees, which provided an effective protective thickness of approximately 90 mm against incoming projectiles. In stark contrast, the German Panther tank boasted a more robust 80 mm of frontal armor, sloped at a similar 55-degree angle, yielding an impressive effective thickness of around 140 mm. Superficially, when comparing these figures, the Sherman appears significantly outmatched. However, this seemingly inferior protection was a calculated engineering trade-off. Thicker armor inherently necessitates a heavier suspension system, more potent engines to propel the increased mass, wider tracks to distribute the greater weight, and substantially stronger transmissions to manage the amplified stresses. Consequently, the Panther weighed a formidable 45 tons, while the Sherman tipped the scales at a comparatively lighter 33 tons. This crucial 12-ton disparity conferred a multitude of operational advantages upon the Sherman. It could traverse a far greater number of bridges that would prove impassable for the heavier Panther. It was readily transportable on standard Allied flatbed rail cars, simplifying logistical movements. It consumed considerably less fuel, extending operational range and reducing supply burdens, and, critically, it was significantly easier to recover from battle when disabled, minimizing vehicle losses and maximizing combat readiness. The transmission system employed by the Sherman tank, while perhaps less heralded than its engine or gun, achieved a legendary status for a distinct set of reasons. It utilized a Synchromesh gearbox, a mechanism remarkably similar to those found in conventional civilian trucks, which fundamentally simplified its operation. This design allowed Sherman drivers to shift gears smoothly without the need for cumbersome double clutching, dramatically reducing the requisite training time for new crews and concurrently lessening the mechanical strain on the vehicle itself. Conversely, the Panther's transmission was infamous for its inherent fragility and demanding operational requirements. It mandated precise double clutching and a degree of mechanical empathy that was often conspicuously absent among the increasingly poorly trained German crews towards the latter stages of the war, leading to frequent breakdowns and maintenance headaches. Consequently, American tank crews, following just a few weeks of intensive training, could proficiently operate a Sherman, a testament to its user-friendly design. In stark contrast, mastering a Panther demanded months of dedicated experience and practice. This ease of operation was mirrored in its maintenance accessibility, which was meticulously engineered into every panel and hatch. A trained Sherman crew, utilizing only standard field tools, could typically remove the engine in approximately 2 hours. Furthermore, the entire transmission assembly could be extracted for repair in a forward field workshop within a single day. German tanks, particularly the formidable Tigers and Panthers, presented a dramatically different maintenance challenge, frequently necessitating the partial disassembly of numerous surrounding components, merely to gain access to the problematic area. For instance, a thrown track on a Sherman could often be rectified by its crew in a mere 30 minutes, restoring the tank to operational status swiftly. However, a similar incident on a Tiger tank could immobilize the behemoth for several hours and often required the deployment of specialized recovery vehicles, highlighting the profound operational advantage of the Sherman's design. It is imperative to understand that these design choices were not indicative of American engineering incompetence. Rather, they represented a profound manifestation of American engineering genius, specifically tailored for the exigencies of industrial warfare. The astute designers at Aberdeen Proving Ground distilled their strategic imperative into a fundamental question: what factor more decisively influences victory in battle? A small contingent of 10 undeniably superior tanks, or a numerically overwhelming force of 50 merely adequate ones? Their unequivocal answer was the latter. Consequently, they meticulously engineered a tank that could be produced on an unprecedented scale by existing automobile factories, leveraging the nation's immense industrial capacity. While German engineers meticulously crafted what could arguably be described as individual armored masterpieces, American designers deliberately conceived of their tanks as highly functional, mass-producible widgets, prioritizing quantity, reliability, and ease of maintenance above all else. The sheer magnitude of these production figures is, quite frankly, almost staggering, bordering on the obscene. Between February 1942 and July 1945, a period spanning approximately 3.5 years, American factories churned out an astonishing 49,234 Sherman tanks across all their numerous variants. To truly comprehend this scale, consider that this translates to an average output of about 170 Shermans every single month, or roughly 39 tanks rolling off production lines every day ceaselessly throughout the entire duration of the war. Now juxtapose this phenomenal output with Germany's production of its two most renowned heavy tanks. Approximately 6,000 Panthers were built between January 1943 and April 1945, and a mere 1,350 Tiger WA and Tiger II models were produced in total throughout the entire conflict. While Germany's aggregate production of all tank types from 1939 to 1945 amounted to roughly 67,000 vehicles, the United States alone manufactured more Shermans than Germany managed to produce Tigers and Panthers combined by an astounding factor of 8. A closer examination of peak production months further illuminates the colossal disparity in manufacturing capabilities. In December 1943, American factories achieved an astonishing feat, completing 2,200 Sherman tanks within that single month. This translates to a staggering rate of one Sherman rolling off a production line somewhere in America, approximately every 17 minutes, operating relentlessly for 24 hours a day throughout the entire month. Individual contributions from various industrial giants were equally impressive. The Chrysler Tank Arsenal in Warren, Michigan alone was responsible for manufacturing 18,413 tanks between 1940 and 1945, a figure that remarkably surpassed Germany's entire production of Panther tanks. Similarly, the Fisher Tank Division of General Motors constructed a substantial 11,352 M4A2 variants, while Ford's extensive facilities contributed thousands more of the M4A3 model, equipped with its distinctive GAA engine. Even the Lima Locomotive Works in Ohio, a company traditionally specialized in the manufacturing of trains, adeptly pivoted its operations to produce a significant 1,750 Shermans, showcasing the widespread industrial mobilization. Conversely, German tank production, despite its emphasis on quality, peaked at significantly lower volumes and commenced considerably later in the conflict. The formidable Panther tank, for instance, did not even enter serial production until January 1943. By this juncture, the United States had already successfully constructed well over 10,000 Sherman tanks, establishing an early and decisive numerical lead. Germany's most productive month for Panther manufacturing occurred in July 1944, during which approximately 380 units were completed. Strikingly, in that very same month, American factories managed to produce more than 1,600 Shermans, underscoring the vast difference in industrial capacity. The legendary Tiger-Thwaite heavy tank saw its highest monthly output in April 1944, with a mere 104 units produced. To put this into even sharper perspective, the United States was capable of building more tanks in a single week than Germany produced Tiger tanks in its most successful month of production. The profound question then arises, what accounts for such an astonishing and overwhelming disparity in production? The answer fundamentally begins with the sheer, raw industrial capacity of the belligerent nations. In 1943, for example, the United States boasted an output of 85 million tons of steel, a stark contrast to Germany's 34 million tons. This represented a formidable 2.5 to 1 advantage in the most fundamental ingredient essential for tank construction and numerous other war materials. Similarly, American aluminum production reached 920,000 tons in 1943, while Germany managed only 250,000 tons, a nearly 4 to 1 advantage in a critical material vital for aircraft and engine manufacturing. This immense and inherent resource gap was, quite simply, unbridgeable, laying the foundation for Allied quantitative superiority. Furthermore, the contrasting timelines for factory construction unveil yet another crucial dimension of this industrial asymmetry. When the United States identified a need for increased tank production, its response was direct and decisive. It simply constructed additional manufacturing facilities with astonishing speed. A prime example is the Grand Blanc Tank Arsenal in Michigan, operated by Fisher Body, which broke ground in January 1942 and, remarkably, delivered its inaugural tank by August of the same year, a mere 7 months from initial excavation to operational deployment. This colossal facility spanned E1, 5 million square feet, and represented a significant investment of $37 million entirely funded by the government. In stark contrast, Germany found itself largely unable to establish new tank plants by 1943, primarily due to the relentless and highly effective Allied bombing campaigns that systematically targeted any substantial construction projects. This strategic aerial interdiction compelled German manufacturers to fragment and disperse their production into smaller, inherently less efficient, and more vulnerable facilities, further hampering their ability to match the Allied output. The German war machine, despite its early successes, found its aspirations of industrial parity severely hampered by a critical lack of available labor and the inherent inefficiencies of its production facilities. By 1943, American tank manufacturing plants were bustling with over 100,000 dedicated individuals, a significant proportion of whom were women courageously venturing into demanding industrial roles for the very first time. In stark contrast, Germany grappled with persistent shortages of skilled workers, increasingly relying upon the coerced efforts of forced laborers and concentration camp prisoners. The output from such desperate measures was, regrettably, characterized by an unavoidable, substandard quality and notoriously poor control over the manufacturing process. Consequently, a Sherman tank meticulously assembled by a well-trained American worker in Detroit exhibited unwavering reliability, while a Panther tank hastily constructed by a starved French prisoner in 1944 was prone to harboring critical, potentially catastrophic, defects. The strategic mathematics of the war proved unforgivingly harsh for the Axis powers. Even granting German tanks a theoretical 3-to-1 kill ratio against the Allied Shermans, a superiority rarely achieved in the brutal reality of combat, the United States possessed the economic and industrial capacity to absorb the loss of 3 Shermans for every Panther destroyed and still maintain an overwhelming advantage in numbers. Germany, conversely, could scarcely afford to suffer any losses at all. By the middle of 1944, American factories were replacing their Sherman losses at a pace that far outstripped the German capacity for destruction, rendering the conflict an insoluble strategic dilemma that Germany simply could not overcome. We invite you to stay with us and watch the remainder of this insightful video. Your support, through a like and a subscription, would be profoundly appreciated. Please also consider leaving a comment below, sharing your place of origin and your thoughts on the compelling topic presented in this video. The sophisticated assembly line techniques employed in the creation of Sherman tanks represented Henry Ford's pioneering Model T principles, but amplified and intensified, specifically adapted for the demands of welded armor fabrication. An observer stepping into the Chrysler tank arsenal in Warren during 1943 would have witnessed not merely traditional weapons manufacturing, but rather a meticulously coordinated industrial spectacle, akin to a choreographed ballet of machinery and human effort. The initial stage involved flat steel plates, robust 5-inch thick armor, arriving directly from steel mills, precisely pre-cut to stringent specifications. These formidable plates were then conveyed to colossal stamping presses, machines capable of exerting an astounding 2,000 tons of pressure, thereby reshaping robust metallic sheets with remarkable ease, much like one might bend thin sheet metal. The role of the press operator in this innovative system did not demand the artisanal skill of a traditional craftsman. Instead, it centered on the precise monitoring of gauges and the activation of levers at exact, predetermined moments. The overarching philosophy emphasized subassembly as paramount. Rather than constructing a tank sequentially from front to back within a single location, the Sherman was fabricated concurrently across a multitude of specialized, dedicated production lines. One specialized team diligently worked on the transmission assembly, while another was responsible for manufacturing the intricate turret basket. A third group meticulously constructed the suspension bogies, and a fourth independently assembled the engine compartment. Each of these discrete subassemblies was then transported, either via overhead conveyors or rolling platforms, to the main production line, where all the individual components ultimately amalgamated. This ingenious arrangement meant that progress was never halted while one group awaited the completion of another's task. Instead, every team worked simultaneously on different tanks, each at varying stages of completion. It was within the welding operation that automotive thinking truly fundamentally transformed the landscape of tank production. A single Sherman hull necessitated approximately 5,000 separate welds to securely join all its armor plates. Conventional shipyard or arsenal welding practices typically relied on exceptionally proficient welders, individuals capable of executing any joint at any angle. Chrysler, however, ingeniously categorized these 5,000 welds into distinct types: flat welds, corner welds, overhead welds, and so forth. They then implemented a rigorous training program, specializing workers in just one specific type of weld. A specialist in flat welds, for instance, might execute the identical weld 200 times within a single shift, thereby attaining unparalleled rapidity and uniformity that a generalist welder could simply not match. The strategic deployment of jigs and fixtures effectively removed any element of conjecture from the manufacturing process. The base of the lower hull, for example, rested securely within a massive steel fixture, which held the floor plate, side plates, and sponsons in perfect positional congruence while welders performed their tasks. These fixtures were engineered with astonishing precision, accurate to within 1/1032 of an inch. Workers were thus relieved of the need to measure angles or verify alignment. The jig performed these critical functions autonomously. This streamlined approach enabled Chrysler to recruit and train welders in a mere 6 to 8 weeks, a stark contrast to the protracted, multi-year vocational training that German firms traditionally demanded. By 1943, the average tank welder at Chrysler was a civilian of just 90 days prior, demonstrating the remarkable efficiency of these accelerated programs. The intricate turret assembly process unfolded on sophisticated rotating pedestals, which afforded unrestricted visibility and reach to all sides of the component without the need for manual repositioning. Workers meticulously installed the gun mantlet, mounted the powerful 75mm cannon, integrated the recoil dampening system, affixed the gunner, used periscope, and connected the traverse motors, all while the turret rotated slowly and steadily on its powered stands. This highly efficient station-based approach ensured that each worker remained in a fixed location, with all their necessary tools readily accessible. This eliminated wasted motion, such as walking back and forth to tool cribs or fruitlessly hunting for parts. Instead, every required item flowed directly to them. Final assembly served as the ultimate nexus of integration for the entire tank. The completed hull arrived on specialized rails, while powerful overhead cranes precisely lowered the engine and transmission, which had been pre-assembled and integrated as a single, cohesive module. A team of 4 workers expertly guided this power pack into its exact position, while other technicians concurrently installed the drive shaft. The entire power pack installation, a process of considerable complexity, took approximately 45 minutes. This stands in stark contrast to German tank plants, where engine installation was often a protracted, labor-intensive undertaking, frequently requiring custom fitting and extensive adjustment throughout an entire day. Subsequently, the turret, already fully equipped with its gun, ammunition racks, radios, and crew stations, was precisely lowered onto the hull ring. The entire final assembly process, from a bare hull to a fully operational running tank, consumed a mere 8 hours. Quality control was not relegated to a final end-of-line inspection, but was meticulously integrated at each individual production station. Inspectors, utilizing specialized go-no-go gauges, unremittingly checked welds for consistency and integrity. Should a weld fail inspection, the worker responsible was required to redo it immediately, preventing the defect from progressing to the subsequent station. This proactive strategy identified imperfections at their nascent stage when they were considerably cheaper and easier to rectify. By the time a Sherman tank reached the test track, it had undergone dozens of rigorous inspections. The German methodology, conversely, involved inspecting completed tanks and subsequently necessitating their partial disassembly to address any identified problems, a methodology that proved disastrously unproductive. The dedicated individuals who constructed the impressive fleet of 49,000 Sherman tanks were not the workers anyone might have initially anticipated. In 1940, American factories predominantly employed Caucasian males, many of whom were immigrants or the descendants of immigrants, possessing industrial experience passed down through generations. However, by 1943, the composition of tank plants had profoundly altered. Women constituted a remarkable 40% of the workforce at Chrysler's tank arsenal. African Americans now held positions previously reserved exclusively for whites, and even elderly workers who had retired years prior returned to the production lines. The societal metamorphosis within American manufacturing facilities proved as groundbreaking as the sheer volume of output itself. The iconic image of Rosie the Riveter was not merely propaganda, but a statistical reality. Women entered the realm of heavy manufacturing in previously unimaginable quantities primarily because a vast proportion of the male workforce had departed for military service. Between 1941 and 1945, the military conscripted an astonishing 16 million Americans, thereby creating severe labor shortages that would undoubtedly have severely impaired industrial output had it not been for one crucial factor. Women stepped in to fill these critical voids. At the Fisher Tank Arsenal in Grand Blanc, Michigan, women were observed operating 20-ton overhead cranes, managing powerful stamping presses, and performing intricate welding tasks on armor plate. These were by no means light assembly jobs. They were arduous and strenuous roles, demanding significant physical exertion, including lifting, climbing, and working with inherently dangerous equipment. The comprehensive training programs implemented were noteworthy for their streamlined effectiveness and concise duration. The War Manpower Commission took the initiative to establish extensive engineering, science, and management war training programs at universities and vocational schools across the entire nation. A typical welding course, for instance, spanned a mere 6 weeks, with students attending 6 days per week, 8 hours per day. Participants diligently practiced on scrap steel until they could produce consistent, high-quality welds, after which they graduated directly to the factory floors. Training for machine operation followed a similar model, comprising 4 to 8 weeks of rigorous pedagogical sessions focused on lathes, milling machines, or drill presses. The deeply ingrained notion that skilled manufacturing necessitated years of apprenticeship entirely dissipated in the crucible of wartime imperatives. Production shifts ran uninterruptedly, without cessation, in 3 distinct 8-hour rotations. The inaugural shift commenced at 7,000 a.m., the second at 3,000 p.m., and the third The nocturnal production cycle began at 11,000 p.m. This meticulously planned schedule ensured that tank plants maintained continuous illuminated operation. As one crew departed for home, another arrived within minutes, seamlessly picking up precisely where the previous shift had left off. Workers assigned to the third shift, often referred to as the graveyard shift, received a 10% differential in their pay. Though recruitment for the midnight to 8 a.m. work block consistently remained challenging, factories thoughtfully provided cafeterias that operated 24 hours a day, acknowledging that tired, hungry workers were more prone to making mistakes that could ruin a tank hull worth thousands of dollars. Housing rapidly escalated into an immediate and pressing emergency. Chrysler, S Tank Arsenal, at its peak production, employed an astounding 25,000 workers. Yet, Warren, Michigan, was fundamentally not a city equipped to accommodate such a sudden demographic explosion. The Federal Public Housing Authority responded by constructing emergency housing projects, including basic apartments and dormitories, which were erected with remarkable rapidity, often within a matter of months. The Willow Run Housing Project, situated near Ford S. Bomber Plant, became particularly notorious for its 3,000 trailers and temporary housing units, which were unceremoniously crammed into waterlogged terrains. Workers frequently shared bedrooms on opposing shifts. One slept while the other worked, a practical arrangement known as hot bunking, a term borrowed directly from naval practice. While the remuneration was considered good by the austere standards of the Great Depression, it was certainly far from luxurious. A tank welder in 1943 earned approximately 90 cents per hour, amounting to about $37 for a standard 40-hour week, augmented by overtime pay. This sum, when adjusted for inflation, would equate to roughly $650 per week in 2025, representing a respectable income, indicative of a stable middle-class lifestyle. Regrettably, women often earned less than men for identical work, typically receiving only 60–70% of male wages, although this still represented a marginal improvement over antecedent inequities. African American workers faced similar disparities in remuneration and were frequently assigned the most arduous, dirtiest, and most dangerous jobs, such as foundry work, sandblasting, and heavy lifting. Workplace injuries were common occurrences and frequently severe. Metalworking, by its very nature, is intrinsically perilous. Moving machinery, heavy components, molten welding slag, and overhead cranes carrying loads weighing several tons all presented constant threats. The Bureau of Labor Statistics documented over 37,000 workplace fatalities in American factories between 1942 and 1945. Tank plants, in particular, reported higher than average injury rates due to the immense weight and sheer size of the components involved. A dropped armor plate, for instance, could cause instantaneous fatal injury to a worker. Welding in the confined spaces inside tank hulls frequently led to severe burns and the inhalation of noxious vapors. Despite these pervasive dangers, turnover at tank plants remained remarkably minimal once workers successfully navigated their initial 3 months. This impressive retention was fostered by a powerful combination of patriotic purpose, consistent pay, and a strong sense of community among the workers. These individuals deeply understood that their dedicated efforts truly mattered. Every Sherman tank that rolled off the assembly line represented the potential for sons, brothers, and husbands to return home alive. The ultimate defeat of Germany in the Second World War was, in essence, sealed within the vast industrial complexes of Detroit, Warren, and Grand Blanc, long before the first Sherman tank engaged in battle. This assertion is not an exaggeration but a stark, mathematical reality. By the pivotal year of 1944, the German Wehrmacht confronted an insurmountable strategic challenge. While their armored vehicles, such as the formidable Panther and Tiger tanks, demonstrably surpassed their Allied counterparts in individual combat engagements, and their tank crews often possessed greater combat experience, honed through years of relentless conflict, their refined tactical doctrines proved insufficient. These advantages were utterly nullified as they were progressively overwhelmed by an unyielding deluge of American armaments, which arrived on the battlefields at a pace far exceeding their capacity for destruction. The relentless narrative of material attrition paints this picture with brutal, unmistakable clarity. Consider Operation Cobra, the pivotal American offensive that initiated the breakout from the Normandy beachheads in late July 1944. This massive initial thrust deployed an estimated 1,500 Sherman tanks. In the intense first week of engagements, German defensive actions managed to decimate approximately 300 of these American tanks. While a 20% casualty rate might appear catastrophic on the surface, its true significance is revealed when one considers the immediate and overwhelming American capacity for replenishment. Supply depots located across the English Channel swiftly dispatched 450 replacement Shermans to France, ensuring that the U.S. Third Army, spearheaded by General Patton, not only maintained its momentum, but actually accelerated its advance. Conversely, German panzer divisions found themselves utterly unable to compensate for their losses. A Panther tank destroyed on the fields of Normandy was, for all practical purposes, permanently removed from the battlefield. Although German manufacturing facilities might eventually produce a replacement, the formidable challenge of transporting it to the front lines in France, under the unyielding dominance of Allied air power, proved almost insurmountable. We truly appreciate your engagement so far. Please stay with us and watch the end of the video. We would be grateful for your like and subscription. Please also write a comment about where you are from and what you think about the video topic. The logistical dimension represented a critical juncture where the sheer industrial might of America truly crippled the German war machine. A single Sherman tank, for instance, consumed an estimated 150 gallons of fuel for every 100 miles traversed. When this figure is extrapolated across thousands of armored vehicles, constantly on the move, the gargantuan demand becomes apparent. This immense requirement underscores why the United States petroleum industry achieved an astonishing output of 1.5 billion barrels of oil in 1944 alone, a volume exceeding that of all other combatant nations combined. In stark contrast, Germany's domestic production for the same year amounted to merely 40 million barrels, with the majority derived from synthetic processes utilizing coal. Consequently, when Allied bombers systematically targeted and destroyed German synthetic fuel plants in mid-1944, the operational effectiveness of panzer divisions was severely compromised. They literally found themselves immobilized by a catastrophic shortage of fuel. The desperate Ardennes offensive in December 1944, famously known as the Battle of the Bulge, was a high-stakes gamble explicitly predicated on German forces seizing American fuel depots, as they simply lacked the necessary petroleum reserves to sustain and complete such an ambitious operation. Beyond the critical issue of fuel, the profound scarcity of spare parts undermined German operational readiness as thoroughly and devastatingly as direct combat losses. Should a Sherman tank sustain damage, such as a thrown track or a fractured transmission, replacement components would typically arrive within a matter of days from vast supply depots brimming with thousands of essential parts. German tanks, however, were plagued by persistent mechanical failures. The Panther's final drive, for example, was notoriously susceptible to breakdown, failing on average every 150 kilometers in its initial production iterations. Crucially, replacement final drives were simply not available in adequate quantities. German frontline units frequently reported that between 30% and 50% of their armored vehicles were non-operational due to mechanical malfunctions rather than battle damage. This dire situation forced them into the desperate practice of cannibalizing parts from disabled tanks to maintain others, a vicious cycle that inexorably guaranteed a continuous decline in their overall operational strength and combat effectiveness. The robust and comprehensive training pipeline established by the United States illustrates yet another facet of its industrial superiority. American tank training schools located at key installations, such as Fort Knox and Fort Benning, consistently graduated thousands of proficient crews each year, with each individual receiving between 12 and 16 weeks of intensive instruction. This ensured a deep reserve. For every Sherman crew tragically lost in combat, approximately 5 fully trained replacements were readily available stateside. In stark contrast, Germany's training infrastructure had severely eroded by 1944. Replacement crews were subjected to hastily assembled training programs lasting mere weeks rather than months. Frequently, these recruits would never even encounter the specific tank model they were destined to operate in combat until their arrival at the front lines. Such profound inexperience not only exacerbated the inherent mechanical unreliability of German tanks, but also compounded combat losses, as these inadequately prepared crews struggled to operate complex systems properly, leading to more frequent breakdowns and increased vulnerability in battle. The Strategic Bombing Campaign, a monumental undertaking made possible by the prodigious output of American industry, ultimately closed the loop on Germany's fate. The very same factories that churned out thousands of Sherman tanks were concurrently producing B-17s and B-24s by the thousands. These formidable bomber fleets were then systematically deployed to relentlessly dismantle German industrial capacity from 1943 onwards. Critical nodes, such as the ball-bearing plants at Schweinfurt, the vital synthetic oil facilities nestled in the Ruhr region, and the essential locomotive works responsible for transporting supplies were all meticulously targeted. This precision targeting was a direct result of American intelligence, understanding Germany's strategic vulnerabilities. Its war economy simply could not absorb widespread disruption with the same unparalleled resilience as America's. When Allied bombs inflicted irreparable damage upon a German tank factory, that facility remained destroyed. In stark contrast, the United States possessed the industrial depth to potentially lose an entire factory and simply construct a replacement, a testament to its overwhelming economic and manufacturing might. The ultimate reckoning of industrial output presents an unmistakable and stark contrast. Germany, throughout the conflict, managed to produce approximately 25,000 of its most formidable armored vehicles, the Panthers and Tigers, combined. In the same period, America manufactured a staggering 49,000 Shermans. Yet this figure merely scratches the surface of the prodigious American output, which also encompassed 24,000 light tanks, 2,400 heavy tanks, an astounding 89,000 aircraft, and 5,000 vital cargo ships. The industrial superiority was not merely quantitative, it was existentially overwhelming. Germany entered World War II leveraging the industrial capacity characteristic of a regional power, albeit a highly efficient one. America, conversely, engaged in the global conflict with the manufacturing might equivalent to that of an entire continent. The final outcome, therefore, was never truly in doubt once the vast network of American automobile plants shifted their focus from civilian vehicles to the relentless production of tanks and other implements of war.